Okay, so let's get started. So before the actual lecture, a few announcements. As you hopefully know, today is the day to choose part 3 or topic for part 3 of the project. So this will be the following lecture will be introducing traffic safety and traffic efficiency communication in that respect. And then you have the choice of these 4 topics: e-health, ICT for power engineering, the previous one which was more on control over wires or over communications, and now traffic safety, which will be more focused on wireless, while the former was on wired networks. So the selection can be done today. I think it starts at 3 o'clock. Now we have a limited number of slots per topic, so it's going to be on first come, first serve. So if you have a very specific wish of a certain topic, maybe you should be on the ball here. Okay, so let's continue to talk about the issue today, which is on traffic safety. Traffic safety is what it is. It's about enhancing, reduce the number of accidents and fatalities and injuries in the road traffic. So the question I would like to pose here before we start is that why should we be interested in this? Is this a big problem or not? So I have a question here. So how many people do you think dies out of car accidents or traffic accidents globally per year? Okay, so count the number of deaths yearly globally, and order of magnitude is fine. So is it 10,000, 100,000, 1 million, 10 million, 100 million, 2 million, 10 million, 10 million? 1, 2, no. So yeah, the answer is a few years ago it's 1.3 million. Okay, so this is from the World Health Organization 2012. So 1.3 million. How many people have died of the coronavirus? 100? I think it's more on the 1,000 level, right? But I mean, here we have a killer which is with us year out and year in, right? And so, of course, efforts are being made to reduce this, but maybe this is not getting as much attention as one of these pandemics. Okay, now the pandemic can, of course, has the potential of wiping out the human population, so maybe we should be concerned about this, but we have also other problems to deal with. Okay, so part of the solution to this is many things. We could, for instance, wear seat belts. We can avoid drinking and driving, and we can make the road infrastructure better and so forth. So there are many things one can do, but one thing one can also do is to introduce communications to enable what we call cooperative traffic safety solutions. So these cooperative intelligent transport systems, CITS for short. Okay, so there are new and fancier acronyms for this, but CITS has been around for a while. Maybe next year I will change this to the latest acronym. But it's this one is essentially dividing applications into 2 broad categories. We have traffic safety, which is to avoid accidents, and we have traffic efficiency, is to use the roads more efficiently. Here we would like, avoid accidents essentially. Traffic efficiency is perhaps to enable platooning, which is driving very close to each other. And if we do that, of course, we reduce the fuel consumption due to the air drag. Actually, fuel consumption goes down even for the lead vehicle in this, which is a little bit surprising. But everybody gains here. And by packing the vehicles more densely here, we don't need more lanes, so we don't have to build wider roads. Okay, so we can use, and we can perhaps do with the more tighter lanes also. And building roads is a huge investment and also drives carbon dioxide emissions and whatnot. In particular, all the concrete needed for this is a big contributor to carbon dioxide. Anyway, so we would like to do this, and we would like to do that using communications. So we want to use V2X communication. V stands for vehicles. What is a vehicle? Well, the most common one is like cars, I would say, but it could also be buses and trucks, but also construction equipment. So all of these type of vehicles would benefit to communicate with each other in order to solve traffic safety and traffic efficiency applications. And as a matter of fact, I think a field where we see this first deployments will be in the professional sector, where you have like in a construction site or in a closed-off area like a mine, for instance. You can have better control of who's there and better control of the vehicles and so forth. And so it's more controlled environment, so it's easier to deploy V2X communication and, or rather not to deploy it, it's not easier perhaps, but it's easier to use that in order to control things. Yes, okay, but the X then could be of course another vehicle, but it could also be road infrastructure and something called VRUs. So road infrastructure could be these smart traffic signs with adaptive speed limits and so forth. And this is also to, facilitate maximum throughput on the roads we have. So sometimes it's better to drive slower than faster to improve throughput on a road. And the reason for this is that when one drives fast, one has bigger gaps because it's scary to drive fast and close, for instance. So it's not obvious that we should drive faster in order to improve throughput. Yeah. And then, of course, one should obey these, which nobody does, but that's another issue, right? But this is one thing, road infrastructure. It could be the old smart, and it could be old-fashioned stupid, right? But also here, it would be beneficial if these traffic signs would inform the environment about the phase of the light. I mean, how long will it continue to be green? And then you can plan your driving accordingly, right? Or if it's red, it's going to be green in, say, 5 seconds or 10 seconds, and then I can plan my driving accordingly to avoid too many stops and accelerations in the city. So that would be beneficial. And then vulnerable road users are people like this, which are moving around in the environment, perhaps plugged in and not watching anything, and this is could be roadkill, who knows? But we have these going around, and also bikes, and whoever is not protected but is using the road is called a vulnerable road user. Cyclist is a prime example of this. So we would like to protect these. So when it comes to communication, so if we have vehicles that needs to do traffic safety together, for instance, they need to share information with each other and the road infrastructure. So of course we need communication, and we cannot use wires, and that's because vehicles are moving around. So when it comes to mobility, we are basically forced to use some type of wireless communication, and then there is radio, and then there are other technologies. Other technologies could be infrared and so forth. I will just skip the infrared stuff because it is used in certain contexts, but not so heavily, I would say. So let's concentrate on radio. Okay. Now there are state-of-the-art systems which are state-of-the-art, meaning that they're ready to deploy today. These could be put on the market today for this V2X communication. Now I put direct here, meaning that we can transmit information directly between one vehicle and another without going through some intermediate nodes. There are two main systems for this, something called ITS-G5 in Europe and something called DSRC in the US. The names are not super important, but that's what they are called. The interesting part is that both of these systems use the same medium access control and physical layer, and the one which is based on a standard called IEEE 802.11p. The upper layers, the network and application layers and so forth, are different, and transport layers are different in the Europe and the US. But we'll not talk much about that today. However, this 802.11, you might recognize this as the family of standards for Wi-Fi. So essentially, this is a Wi-Fi standard that's been adopted for V2X communication. However, the big change is not so much. So the only really major change between 11P and your regular Wi-Fi, what is that? Well, it allows communication which is outside the context of a BSS, which is completely mystical phrase, right, if you don't know Wi-Fi. But what it means is that we can start to communicate with each other without first logging on to a network, forming and logging on to a network. And the reason for this is that it takes some delay to join such a network. So when I open up my laptop, I don't have instant access to the network. It will, take anything from a few seconds to 30 seconds before I'm connected. Okay, and that is not acceptable if we're want to do traffic safety where latency is an important thing. So the physical layer is the regular Wi-Fi, I would say. So the 11.11 standard has, 5, 6, 7 different physical layers. But the most dominant one today is called OFDM. So the physical layer in 11P is also using OFDM with 10 megahertz channel bandwidth, which is a little bit different because regular Wi-Fi use 20 megahertz. So that's a small difference also. And the default system data rate is 6 megabits per second. So if you heard earlier today about these wired buses and networks in cars, you have them from a few kilobits per second up to maybe up to a gigabit per second in that range. Now here, this is sort of like in between, it's 6 megabits per second. But this needs to be shared then of all the vehicles which are in radio range of each other. So that's actually a bottleneck today. And efforts are done in order to remove this bottleneck by updating the standard. So efforts are ongoing as we speak. Okay. Data traffic models, and we heard this also earlier today. There are basically two types of things. There's something which is event triggered and something which is time triggered. So the same thing occurs here. We have periodic time triggered data traffic, and we have event driven data traffic. Event driven happens when an event occurs. Periodic or time triggered is every 100 milliseconds or something, then you transmit a new packet. Okay, these are the data traffic is typically broadcast, which means that the transmission, the data should go to all the vehicles which are in the vicinity, and at the same time we are also receivers of this information. So it's like a broadcast situation. So broadcast means that all nodes are simultaneously receivers and transmitters in this situation, which makes it a little bit tricky to do this. At least it's a twist to it. Payload size, the data payload is about 400 bytes long. So a regular IP packet is how long? Do you know? Regular IP packet is typically 1500 bytes long. So this is like a third of a regular IP packet. So it's relatively short compared to this, but 400 bytes is a sizable chunk of data. So what is it? 4 times 8 is 2,400 bits, something like this. Okay, now the repetition rate here in the periodic one is 1 to 10 hertz. So once per second or once per 100 millisecond or something like that, in that order. And this is actually decided on a little bit on the requirements. So just to illustrate this, if we have a network here with 4 vehicles, we have data going from this one to all the others, and from this one to all the others, and this one to all the others, and this one to all the others. And this needs to happen in some type of controlled fashion. So we need some way to share the channel in a smart way for this, not for the packets not to collide. Because you heard today that in this automotive Ethernet, you can transmit full duplex over one single channel. If you can subtract off your own signal when you're transmitting, what remains is the signal from the other user. So this is called signal cancellation and so forth. This is extremely difficult to do in radio, even though that there are experimental systems for this. This is not, it's relatively far from being deployed in this type of situation. So here, basically, if there is a collision, there is a big chance that we lose the packet. So this needs to be avoided. One twist of this broadcast communication is that retransmission protocols are difficult to do. And the reason for this is that when we want to transmit here, it's actually 3 receivers. So how should we organize the acknowledgements from these receivers? Right? Then each of them would like to transmit an acknowledgement back to this one, which is quite a lot of overhead in doing that. And also to do that, if say this transmitter receives an acknowledgement from vehicle 1 and 2, what should we do with vehicle 3? Should we retransmit this again, and what happens with the acknowledgements then, and so forth? So it's basically a messy thing to do here. So what has been decided is not to do it easily. So it's very interesting that retransmission protocols are not used for this traffic safety things. And retransmission protocols is our main vehicle to get reliability. Okay, so we are throwing that out of the window and have to rely on reliability from other sources. So reliability is not easily guaranteed here. Okay, and I mean, if we look then, is this a problem that reliability is not easily guaranteed? Well, when it comes to these time-triggered data traffic, then consecutive packets, okay, so these time-triggered packets, what are they? Well, it's basically like a vehicle is driving, and every 100 milliseconds it sends a packet saying, okay, I'm a vehicle, I'm at this point in space, x, y coordinates, I'm heading in this direction, this is my speed, and a few other things. And then 100 milliseconds later, you transmit a new packet saying, hey, I'm a vehicle, I'm at this position, this is my heading speed, and so forth. So obviously, these 2 packets contain similar payloads, not exactly the same payload, but they're quite related to each other. So in that type of data traffic model, it's not catastrophic if we lose 1 or 2 packets. Okay? The problem is if we lose a number of packets in a row, then that could be a problem. But occasional packet losses are not a big problem. Again, then it's not so bad actually as one might think to lose ARQ for this, but we need to somehow still guarantee that every now and then we get a packet through, and we'll talk more about that in a short while. These event-triggered messages are basically when a vehicle is driving and say doing an emergency brake. Then it would like to inform all the vehicles behind it, okay, I'm emergency braking. That's why you have brake lights. Right? But now you do this over radio instead, which has big advantages when it comes to delays and so forth, and in particular for automated driving. Anyways, so when this happens, we transmit the message, I'm braking, okay? And to get up reliability, we just wait a short while and then send the same message again. So when doing emergency braking, we don't transmit just a single packet, but several packets in a row. And we keep on sending these as long as we're doing this emergency braking. So we might send, I don't know, 10 or 20 packets with the same payload. And that increases then reliability. But again, we don't do any retransmissions here, so there is no acknowledgements and so forth. So actually the transmitter is never sure that the message has been received, which is a big disadvantage. Nevertheless, we will still use error detection. So we use CRCs to do error detection. And the reason for this is that the receiver would like to use the CRC to know whether it can trust the received frame or not. If there are errors in the frame, we throw it away, right? It's better not to use data than to use faulty data. Right? So instead of, so that's it, essentially. So communication requirements, it's a little bit then tricky to do this, but what would we like to see? Well, probably we want low delays, probably we want high reliability, probably we want to have good scalability, and we also want fairness. So actually delay and reliability, I will show, is essentially coupled to each other. So that's one requirement in my world. So we have this low delay and reliability. Scalability, we'll talk about that in a second, and also what fairness is. So scalability is in a situation like this, where we have a traffic jam, and if there is a transmitter in each of these vehicles and they send this time-triggered data, every 100 milliseconds each vehicle is transmitting something, we can imagine that there is a message here, and then there is a message here, there is messages all over the place, right? So traffic congestion between vehicles typically leads to traffic congestion of data, communication congestion. So what we would like to do is to make sure that even in a situation like this, we're able to deliver these messages. Okay, so that's scalability. Fairness has to do also with this situation like this, that we let each transmitter have access to its fair share of the channel, right? So we don't prioritize maybe vehicles from a certain brand or something like this. Of course, we might want to differentiate between vehicles. For instance, we would like maybe, say, an ambulance, a fire truck, or a police car to have better access to the channel than regular cars, say. But within one group, say, of all private cars, for instance, we should have a fair distribution of resources. Reliability then, and latency. So here's a very, very simple model of communication from this vehicle to this vehicle. We have an application layer, and there's a protocol stack. At the bottom, we have the physical layer, and above that, we have a layer called the medium access control layer, which is actually a sub-layer in the data link layer. So actually, we will talk more about the MAC layer as starting next week. But anyways, the physical layer, is responsible for transmitting bits over the channel. The medium access layer its responsibility is to access the channel in a smart way. So we try to avoid collisions. We'll talk much more about that during next week. But anyways, since we are using CRCs, any frame that goes over the channel and have errors in it that are detected due to maybe channel noise, channel fading, or collisions, whatnot. If there is an error, then we junk that, right? We never use that. So from application to application, we can think of communication as being consisting of two things. Either we lose a packet, or if we get the packet, it's error-free. But when we get the packet, which is error-free, it has a certain delay also, of course. Okay, so from an application point of view, either we get a packet and then it's fine, or we don't get a packet. If we get a packet which is error-free, then it has a certain delay associated with it also, depending on what the delay is over the channel. So here's the conclusion there. If we have perfect error detection, let's assume that, then no erroneous payloads would ever reach the application at the receiving end. So with this convention, we can say that packet loss causes a packet. If we think of a packet loss to have infinite delay, then this channel from here to here is completely characterized by the delay statistics. And if so, we can define reliability in terms of this. So an example might be easier to understand here. So here we have a time axis, and we have a data generation process. And here is like, let's think of this as this time triggered, or event triggered. At some point in time, a timer expires and we generate a packet, or an event occurs and we generate a packet. And this packet then needs to be transmitted. So in the blue one here, we generate packets, and in the red one here, here's when packets are actually delivered. So at some point, let's call it T0, a packet is generated, and it's put down into the MAC layer, and then down to the physical layer, over the physical layer, goes over to the other side, and maybe there is multi-hop here also, I don't know, but at some point, it will be delivered, hopefully, right? So the time between, okay, and let's say that the delivery time is T0 prime, so the prime for delivery. Okay, so the difference between these two times is what's known as the end-to-end latency or end-to-end delay. And this might include ARQ if we had ARQ retransmission protocols or whatever you like to have here. Now, I just told you that in 11p ARQ is not used, but maybe in the future it could be used, who knows. But at some point a packet is generated, and at some later point it is delivered. And the difference between these two times is the latency, what we call the latency. Okay, and then there is another packet being generated, there is another latency, and there is another packet here. But this packet actually gets lost. Okay, so it's never picked up by the receiver, so it's never delivered. So what would be a reasonable latency for this, you think? Infinite. Very good choice. So let's call a situation when a packet is lost, we essentially assign infinite delay to this one. It's never delivered, or it's delivered at infinity, but then the universe has collapsed and we don't care, right? It's of no use to us. Okay, and then there is a third packet and so forth. But we see here that we can characterize this is sort of like a random process where we have random delays, and every now and then we have infinite delays. So we might be interested in controlling these delays so they're small enough in some way. There is another metric also that we're interested in, and that's called okay, so before going to that. So latency, we should use this, and I will motivate this later on. I think it should be used when messages are unrelated. So this will be like, for instance, this emergency brake situation where it's event triggered. But there is another metric which is also of interest that deals with latency. It's something called age of information. So let's, what is that? Well, we know that the packet was generated at time t0 and it was delivered at time t0 prime. So at time t0 prime, from the receiver's perspective, it received a packet which has some initial age. Okay? The age it has is exactly tau 0. I mean, the time it took from when it was born until it was delivered. So at the time of delivery, the receiver has a packet whose age is tau 0, sorry. And then as time goes, the age of that increases linearly, right? So this describes how the age of the latest received packet increases over time. And it increases over time until the next packet is delivered. And the next packet is delivered at time t1 prime. So at time t1 prime, the receiver has now access to a packet whose age is equal to the latency of that. So the age of the latest packet increases linearly until we get a new packet, and then we drop down to the age of the latest received packet. And then we continue like this. And a packet which is never delivered will not affect the age of the latest packet, right? So it will look something like this. We have this sawtooth going up and down like this. And this process would also be interested to limit somehow. We can, for instance, want to limit the peak of this, which is known as the peak age of information. So this is what we would like to control in this case. And my contention here is that age of information is a great metric to use when messages are related. When somehow this is the age of the latest information I got from a vehicle about its heading and speed. Okay. So, and of course this is interesting for me because if I know exactly where all the vehicles are, I can plan my driving accordingly. If I don't know where they are, or uncertain where they are, I need to take precautions and maybe even stop, which is not so nice. So we would like to control this age of information and perhaps this the peak here, so A1, A2, A3 and so forth, or we would like to control tau 0, tau 1, tau 2 and tau 3 and so forth. So how can we formalize this in mathematics? Well, if we think of the delay tau, the latency, to be a random variable, I can compute its CDF, which is the probability that the random variable is less than some x, where x is the value along this axis. And the probability, these CDFs are always increasing and then they flatten out after a while. Regular CDFs that you've probably seen in the past flattens out at 1, but it will not do that in this case. And why is that? Excellent, excellent. So there is a probability that the latency will be infinite, and that probability is non-zero typically. So the difference between the 1 and the asymptote of this is the probability that tau is equal to infinity, which is exactly when we lose a packet. So this is the probability of a packet drop, that we never get it. So from this CDF, we can distinguish between reliability. We can see packet drops in the latency if we do it like this. Okay, and then some person at a company told me, okay, so for my application, I want to have packets which has a maximum latency of tau max. So this is known as the deadline. And then we just read off. I design a system and get a CDF and then read off what is the probability that tau is less than the deadline, and this is what we call reliability. Okay. So here, of course, if tau max is a little bit more relaxed, we can get higher reliability, or conversely, if we want to have very high reliability, then we typically pay for this with latency. And this is almost universally true. If I have a lot of time, I can get reliability, typically through retransmissions or smarter coding and whatnot. If I don't have much time, I don't have time for these retransmissions, and I cannot encode so much, and therefore I have to live with higher probability of packet drop, and reliability goes down. Okay. And then we can do designs, and our design goal is to make the reliability, this number, higher than the requirement. Okay, so the application engineer would give me, as a communication engineer, two numbers, tau max and the minimum reliability required. And then it's up to me to design a system that fulfill this. Okay. Very similar things can be done in terms of peak age of information requirements. So basically, it's completely analogous to the first one, so I'll skip the details here. But my point is that for some applications, this is a good way of doing it. For other applications, this is a good way to do it. This one is more for event-triggered, and this one is more for these time-triggered systems. Okay, but then, what are these requirements? Remember, we wanted the reliability and some we wanted requirements on reliability and latency, or reliability and peak age of information. maximum peak age of information. So if we then concentrate on latency here, so in general one can say we have requirements on this. And this is not rocket science. Every communication task has a maximum latency. Right? What could it be? Could it be 100 milliseconds? Could it be 1 second? Could it be 2 hours? 10 days? Well, it depends on the application, right? So if you do gaming, for instance, you want to have very short latencies. If you send an email, maybe you can live with a few seconds of delay. If you send something to the tax office, maybe you can live with two days of delay. Or maybe not, actually, it was a bad. But if you send something else, right, there could be different latencies. But we always have a latency requirement. But for C2 ITS here, that in many cases we have latency requirements, and then reliability could sometimes be very high, but not always. And latency could be low, but not always. So it's a little bit of a mixed bag of requirements here, I would say. We have bigger requirements on security, but we'll talk more about that later on in the course. So when we started to think about 5G, which was maybe 8 to 10 years ago, Chalmers took part in one of these big projects that defined this, and that project was called METIS. So in METIS, me and my colleagues, we were interested in putting out a system that could meet these requirements for V2X communications. So of course, the first thing to do was to figure out what are the requirements. And then what we came up with was the following requirements: a maximum packet error rate of 10 to the minus 5, 1600 byte long packets, and 5 milliseconds latency. These are super strict requirements, I would say, and not at all required for all applications in the field. As a matter of fact, I'm not sure if there is a single application that requires this because it's so demanding. So I think more normal requirements would be like 10 to the minus 3 in error rate, maybe 400 byte and 100 milliseconds, or something on that order, relaxed in all of these three things. So, but I would like to say that the real requirements are very poorly understood in the field. And the reason for this is that we don't have so much experience to put up good requirements here. So there's a lot of guesswork going on. And that's what you do. When you don't have information, you have to guess. And so make the best guess with your current information. So whenever you read about these requirements, you should be a little bit careful in interpreting these as absolute requirements. They are more like the current guesswork, I would say. All right. So let's move over to another, actually a $1 million question. So I don't know if you recognize this, but this is a picture of the Oracle in Delphi. It's a German, so it's here in Fraktur here. So this is the Oracle of Delphi, where the ancient Greeks went to and ask questions of fundamental importance. Should we invade, should we start a war against the Persians, for instance, and if you did that, you typically got your butt kicked, and so you don't want to do that on a regular basis. So you want to go to the Delphi here and ask, okay, so should I start a war or not? And here the question is, like, should we use 11P or should we use cellular for V2X? So then if we go to the Oracle of Delphi with this question, or if we should invade Persia, the Oracle, this lady who's sitting here above here and gets some magical vapor through her body, and then she answers, right? And she answers the following: it depends. That's typically actually also the response one got from the Oracle in Delphi. It was very ambiguous, right? So anyways, you get what you pay for. So it depends. So let's see what is good and bad about cellular compared to 11P. So for some of these ITS applications, the latency, reliability, and availability provided by 3G and 4G will be sufficient. We can run this over 4G, no problem, right? So one has seen that in live systems, about 100 to 300 milliseconds latencies have been achieved. But the problem with cellular is coverage. Okay, in particular in rural areas, there is poor coverage. Okay, and that's not good. We would like to have traffic safety also in rural areas. And also to meet more stringent reliability and latency requirements, we need to do something in cellular, and we have done. Okay, so the regular communication when it comes to over cellular from a vehicle here to here. So here's the logical flow of data. It goes through an uplink and a downlink. Uplink to a base station, and then downlink in another base station or the same base station. But anyways, it goes up, gets a little bit processed here, and then goes down. Okay, and this of course is not ideal from a latency point of view. So an innovation in 4G and 5G happens basically at the same time was that, okay, if we have this flow, why not send the data directly? So if we have two vehicles which are in proximity of each other, that is, they are in radio range, why should we go up and then down when we can go direct? So this has been a new thing in 4G and 5G, and it's called side link. So here we have uplink, downlink, and now side link. To coordinate the transmissions of these side links, we can either use a base station to coordinate this, to do the scheduling, or we can do this in a distributed way or autonomous way. The drawback, the good thing about doing this with the base station is that the base station can make a good schedule for us. But if there are no base stations where we are, then we're out of luck, right? So if we have poor coverage, this is not a good solution, and then we would like to do autonomous scheduling. So the work on this has already started in standardization and so forth, and the protocols are getting more and more ready for deployment. No deployment as far as I know yet, but that might change to next year. But I would like to conclude this lecture with the following stuff, is that cooperative intelligent transport systems applications rely on this V2X communication. Now V2X communication, okay, and data traffic is typically broadcast or relatively small packets, maybe a third of a regular IP packet, but since it's broadcast, ARQ is unattractive or complicated, and it's not sure that we will use that. For sure, we will not use that in the 11P standard. Latency or delay and reliability are important for this. State-of-the-art system for this are based on 11P, because this is what's available today. What's available tomorrow will also be cellular systems for this, and maybe there is also a cellular system available today for this. There is a big fight between the cellular industry and the Wi-Fi industry who will win out here. And that fight is not based on facts, but rather on commercial concerns. So when you read about this, when you read somebody at Ericsson says, well, the Wi-Fi standards are crap, cellular is great, you can find something from another Wi-Fi company that say exactly the opposite. So we cannot really trust any of these things. So it's up to, and academics are somewhat trustworthy, more trustworthy, I would say, in this, right? But anyways, when you read about this, you will hear conflicting things, right? And we'll see in a few years who's going to win out of this. So any questions before we break? No? Okay. So remember now to sign up for the topic of your third part of the project today, and then you should be able to start working on this now. We're now in week 4, which means that there is not so many weeks left before the deadline of the project and exams and all these things. So if you have not completed part 1 and part 2 of your project right now, maybe you should start to speed up a little bit. Okay, so that's it. All right, thank you.